will start by giving a quick outline of this talk. So first, I will briefly describe our company, Nano Academic Technologies, and give us a very short overview of our products. I will then present a slide on the technological background, which is spin qubits and semiconductors. I will then motivate the tool Qtcad, present the workflow of the software and the models that are included in the software. There will then be a live demonstration, and time permitting, I will also present a more advanced results of a more advanced simulation on an industrially fabricated quantum dot device, which was published recently in collaboration with ST Microelectronics and Institut Quantique from University of Sherbrooke. And I will then conclude with the current status of the project and potential collaborations. So let me start with the company. So Nano Academic Technologies is a small company based in Montreal. We have roughly 15 employees, mostly physicists, computational physicists, but also engineers and software developers. We are a spin-off from McGill University, founded in 2008. We are actually located right in front of the McGill campus. And our positioning is traditionally molecular quantum transport and atomistic modeling software, which we have been developing for more than 12 years. Ultimately, what our tools enable to do is to predict materials properties and device performance before fabrication or also in the analysis of experimental results. We offer many services for several markets. So our customers are mostly R&D teams for academic, government labs, and private or industrial companies. We have a network of distributors all around the planet, and we also have several types of licenses that we offer for our products, either single users, research group, or cluster HPC licenses. We propose free trial periods of our products, and we continuously improve and maintain our tools with typically releases every 6 months with new features. And also we propose expert scientific consulting services on atomistic and quantum physics projects. Our traditional tools are illustrated here. We are talking here of NanoDecal and Rescue. NanoDecal is a quantum electronic transport tool which works from first principles. So the idea is to solve for self-consistently the density functional theory and non-equilibrium Green functions for a specific device and calculate transport properties, including the effect of each atom and also including quantum mechanical effects, such as quantum confinement. So this way, it's possible to calculate current flowing through, for example, this molecular transistor, including the effect of every little atom there in the channel. So for example, if you put in an impurity, you're going to be able to see its effect. On the other hand, we also have Rescue. We also offer Rescue, which is a large-scale density functional theory solver for material simulations. So Rescue enables to solve systems comprising thousands, if not tens of thousands of atoms. To our knowledge, it's the tool on the market for Cone-Sham DFT that allows to simulate the largest systems. So this is useful for materials design and simulation in many situations, such as interface problems, structure optimization and design, or the design or analysis of advanced materials, such as graphene. There are many applications to our tools. I'm listing only a subset here, but molecular transistors, nanostructures, batteries, Raman spectroscopy, STM, alloys, single dopants and defects, and photocurrent calculations are notable applications. These atomistic codes were used in more than 250 scientific publications. In the last few years, we have been leveraging our expertise in quantum mechanics and scientific software modeling to develop a new tool called Qtcad, which is aiming technology, computer aided design of spin qubits and semiconductors. And this is going to be the focus of this talk today. So let me continue with the technological background. Spin qubits and semiconductors. So here I'm illustrating a typical heterostructure that can host spin qubits. So the basic principles of spin qubits are to confine single electrons or holes in gated quantum dots in semiconductor heterostructures, such as this one here. So typically, a collection of material layers is used to produce, to create a potential well, which is created by the heterostructure itself. And this can lead to the formation of a two-dimensional gas of electrons. And then this generates confinements along this Z direction, so the growth axis. And to provide for lateral confinement, electrostatic gates, so metallic gates, are deposited on top of the devices, and various voltage biases can be applied to deplete regions of the 2-deg and form single, double, or triple quantum dots, or even more. And so ultimately, once a single electron or hole is confined, it becomes possible to manipulate its spin to implement qubits, for example, using microwaves, and then perform 2-qubit gates via the exchange interaction between nearby electrons or holes. So there are many technological advantages to spin qubits in semiconductors. First, they are small nanometer-sized circuits, so this, in principle, enables to fit millions of qubits on a single chip. Of course, there are many challenges to do this in practice, but in principle, it could be done. In addition, those devices can be operated at a temperature of 1K, which seems very small, but is actually very large compared to superconducting qubits. And this simplifies a lot the control electronics and heat management. And finally, these devices are the natural continuation of today's semiconductor technologies. And so it's possible to leverage manufacturing capabilities of the semiconductor industry. And so for this reason, the many notable companies are interested in spin qubits and have R&D activities in that field. So this includes most prominently Intel and IBM, but also more recently Global Foundries, ST Microelectronics, and there are also well-funded startups in that field, such as Silicon Quantum Computing and more recently Dirac in Australia. So this concludes the presentation of the brief presentation of spin qubits and semiconductors that I wanted to make. Now let me motivate this new tool that we just released called Qtcad. So first, it's useful to understand the vision behind Qtcad, and this is best done by making an analogy with the situation that is going on in the classical electronics field for many years now. So the classical electronics industry benefits from a well-established hierarchy of simulation software that go all the way from process simulations to circuit simulations and also device simulations. So the idea is to simulate, it's possible to simulate fabrication processes and obtain a 3D representation of the structure that will result from those fabrication processes. And then this 3D structure can be input into a device simulator, such as, for example, Centaurus device, or equivalent cadence, or equivalent Qtcad products, and calculate, for example, current voltage curves for individual or few transistors based on physical models. And then once those performances of few devices are obtained, it's possible to input them in the circuit simulator in which compact models of transistors are used, enabling to solve for chips containing millions of components. So this is actually an integral part of the electronics engineer's workflow used every day by the industry. If you look at the situation in the quantum space, we quickly realize that there is no such well-established hierarchy of software. And a similar hierarchy would be illustrated here. So we could start again from a process simulator. For spin qubits and semiconductors, this would essentially be the same as for classical devices. But at the device simulation level, already things become very different. And the reason is that spin qubits are operated at very low temperatures, at which even converging the electrostatics of the device becomes a challenge with conventional Qtcad tool. The other reason is that the operating principles of the device are completely different and rely on different quantum physical phenomena, namely quantum effects. And so the models that have to be included in the Qtcad tools are very different. So here I'm illustrating some quantities that are meaningful for spin qubits and semiconductors. The idea of a device simulator would be to start from the structure and calculate, for example, chemical potentials of a quantum dot or charge stability diagrams to identify the single electron or single hole regime in which spin qubits can be operated. Ultimately, at the end of a device simulation, one should be able to get a device Hamiltonian that corresponds to a specific structure. And the idea would then to input that in what we call a qubit simulator, in which the evolution of a few qubit system, time evolution of a few qubit system would be calculated using a compact model of the devices, accounting for quantum control pulses applied by the user and also user-defined noise spectra. And ultimately, we could dream of using circuit simulators in which results of those master equation simulations could be input and then simulate quantum computations with maybe tens of qubits. So in this talk, we will focus mostly on the device simulation, which is where Qt Cad is currently mostly involved. To further motivate Qt Cad, let me list some typical issues encountered by nanoelectronic engineers while designing quantum dot devices. So first, it is typically very difficult to engineer a chip that confines single electrons or holes. And even when this is done, it is difficult to make a qubit from a confined electron. And typically, people have to study a large set of devices until they find the desired properties, which is costly in resources, money, and time. And it is also, even once we have a working qubit, it is also difficult to understand the physics behind the experimental data from measurement performance on the devices. So in particular, to understand those physics, people have to design a model specific to particular devices, which is costly in time. Typically, this needs to involve very specialized people like theorists, which may not be available. And so ultimately, there's a lack of general simulation tools for semiconductor qubits. And so our value proposition is to streamline the design process with a reliable all-in-one tool that predicts spin qubit performance before fabrication. And so in that sense, we have released Qt Cad in May 2022. The first version, 1.0, is now available for download on our website. So the free 30-day trial version can be downloaded on our client portal. And you can eventually visit our website to find downloads and video presentations. And to the best of our knowledge, the key Qt Cad features are unique. So let me now present the workflow of Qt Cad and then the models that are used to simulate those spin qubits. So this is the workflow. Typically, a user will first select a spin qubit technology, which could be based on different types of semiconductor devices. Here we are illustrating the FDSOI, fully depleted silicon on insulator technology, which is developed by ST Microelectronics. But one could also consider, for example, FinFETs, gate-around FETs, or more traditional planar structures that are used to realize spin qubits in semiconductors. Once the technology has been selected, it is necessary to create a 3D representation of the structure. This can be done via Gmesh. Gmesh is a free third-party open source meshing software, which also has computer-aided design capabilities and a graphical user interface. So once the mesh is generated, it can be imported into Qt Cad through our flexible Python API. And so the Python API enables to first load the mesh, but also define the materials throughout the structure, the dopant densities, the boundary conditions, and the quantum models to be solved, and ultimately launch the simulations. And then once the simulations are done, the results can be visualized with standard Python-compatible visualization tools like PyPlot or PyVista. And for more advanced 3D visualization, we recommend using ParaView. All of these tools are free, by the way, except for Qt Cad itself. The models of Qt Cad are as follows. I will quickly summarize those models. As you can see, there's a hierarchy of solvers. So first, the device geometry, as I said, in general, can be generated from Gmesh. But for simple or typical quantum dot structures, it's possible to directly import the layout file, the gate layout file in GDS format, and define the heterostructure and design rules from a user-friendly Python API. And so this can really save a lot of time compared with more flexible but more involved Gmesh operations. Once the mesh is obtained and produced, it can be loaded into Qt Cad, and the first step typically is to solve for the electrostatics of the device. So here we define the boundary conditions and apply potentials at each gate. We define the doping densities, and we solve the nonlinear Poisson equation to finally get the carrier confinement potential V of R for electrons or holes. Once the carrier confinement potential is obtained, it can be fed into our Schrödinger solver. Here I'm talking of a single body Schrödinger's equation within K.P theory, so either effective mass theory for electrons or Luttinger-Cone theory for holes. And this enables to get a basis of envelope functions and energy levels. those basis states can then be fed into a many-body solver, which enables to assemble the many-body Hamiltonian, including all the Coulomb interactions at the quantum mechanical level between electrons or holes inside the quantum dot structure. And then this many-body Hamiltonian can be exactly diagonalized within a truncated basis set, which enables to get many-body eigenenergies and eigenfunctions for the structure. So these are very important quantities because they enable to calculate, for example, chemical potentials of the quantum dot, and they can be fed into subsequent solvers. For example, this transport feature, which enables to solve for a master equation for the sequential tunneling regime, for transport in the sequential tunneling regime of the quantum dot system, and get transport peaks and charge stability diagrams, including Coulomb blockade effects in a quantum dot system. This is particularly important, as I already said, to identify the single electron regime in quantum dot systems. Another important feature is this quantum dynamics feature. So here we interface with QuTiP to calculate quantum dynamics and simulate Rabi oscillations in a realistic structure. And ultimately, this can enable to calculate, for example, the Rabi oscillation rate, so how fast can a single qubit gate be done, and also the gate fidelity. So you can see that using Qt Cad, it's possible to go all the way from the device layout to meaningful qubit performance metrics, which really matter for people who design and produce spin qubits or characterize spin qubits in semiconductors. So this concludes this workflow and model presentation. So the next step will be, in this talk, will be the live demonstration. So for this live demonstration, we will be considering a simple but typical structure. Here I'm showing a top view of the gate layout. In red, you can see this is a red rectangle that represents the simulation domain in which we will solve the various models. And in blue, you can see rectangles that represent metallic gates that are deposited on top of the structure. And then the side view, you can see here, displays the material stack for the heterostructure. So this is a very typical gallium arsenide, aluminum gallium arsenide heterostructure. You have a gallium arsenide substrate, a gallium arsenide cap, and in between an aluminum gallium arsenide layer that enables to block electrons, tunneling of electrons from the substrate to the cap. So here I'm illustrating the conduction band edge for the structure. And as you can see, there's also an n-doped layer that enables to bend the conduction band edge and create a triangular potential along the heterostructure axis, which will confine electrons and create a two-dimensional electron gas. Now, the goal here will be to simulate the structure. In particular, we will produce this 3D representation of the device and solve Schrodinger's equation in this so-called dot region in between the gates and below throughout the structure in the z-axis, so in the heterostructure axis, and try to establish if a certain gate configuration allows bound states in this dot region. So can a quantum dot be formed by such a heterostructure? So I will now leave the presentation mode and show you. So let me leave this presentation mode and show you the scripts that we are going to run for this simulation. So this is the directory in which I stored the script. You can see two scripts, device gen, which is going to be used to load the layout and produce the 3D heterostructure, and Poisson Schrödinger, which is going to be used to define the simulation and run it. There are also three directories inside. There's a layouts directory. If I open this GDS file in Klayout, which is a free layout editor, but you can possibly use other layout editors, we can see this is the layout that I showed in the presentation. And importantly, it's possible to save this layout in GDS text file format, which can be parsed by our device generator called device gen. I already saved this, so I'm not going to do it again. And there is a directory called meshes in which meshes will be saved, and a directory called output in which the results of the simulation will be saved. So I will first go into this device generation script and run it. So first, in the scripts, I will comment each block of code this should be relatively straightforward. The first few blocks simply define variables, parameters of the mesh and the geometry of the structure. So the first two parameters defined here are the characteristic lengths, first for the for a uniform background, and then you also have a finer mesh characteristic length for the quantum dot region, so the region in which we expect the quantum dot to be formed. I also define here the thickness of each material layer. So if I go to the presentation, these layers, so these correspond to the thicknesses here. So I'm actually showing them here, 10 nanometers, 15 nanometers, etc. And I also define a number of mesh points along the growth axis. So these characteristic lengths actually refer only to this XY plane. And these number of mesh layers corresponds to the Z axis, so the heterostructure growth axis. The next block of code will simply define an input and output file for the layout. So the input file is this GDS text file that I just showed how to produce. And the output file is the geometry file that will be produced once this layout is converted into GMesh format. Then the next step is to instantiate a device generator based on these input and output files, and also specify a base characteristic length for the mesh. So if I run the script, you will see this opens a GMesh GUI. You can see that this is simply the layout, and I can also show the mesh that corresponds to this uniform background that we just defined. The next step will be to label the surfaces that correspond to each gate. So top gate 1, top gate 2, top gate 3, bottom gate 1, bottom gate 2, bottom gate 3. This is important because we will need those labels to specify boundary conditions when we you run the script for Qtcad simulations of the structure. So if I close, it will show again with this view command the structure. I could show the labels, they would be changed to those values that we just defined. And then this is where the non-trivial stuff happens. Here we're defining each layer of the structure, the cap, the barrier, endope layer, etc. So simply we define a thickness for each of those layers. We define a dopant density, if any, and also a label that will be used to specify the material in the Qtcad simulation. So if I close the window, it's going to go to the next call of the view structure. You'll see now we have a 3D structure, and something else that I forgot to mention is in this block of code. Here, we have also defined a dot region, so this rectangle here, which represents the region in which Schrodinger's equation will be solved to find if there are bound states in the quantum dot. There are many reasons why we do this. The first is that we might need better precision, so finer meshes in the region in which we solve Schrodinger's equation. Another reason is that solving Schrodinger's equation is more expensive than Poisson's equation, so we don't only want to do that in a small subset of the structure. And finally, if we solve Schrodinger's equation, we're going to find the lowest energy levels, and those levels may correspond to states that are confined. There could be global minima outside the quantum dot region that we want to study. So this is why we define the quantum dot region here. And then ultimately, the last block of code, I label the bottom surface of the structure to define a back gate, and save the mesh in this gated.msh file. So I will now close this, and if I move to this meshes folder, you can see that I now have a mesh file. So the next step is going to be to run the Poisson Schrödinger script. So I will run it now. So again, this is, sorry about this, wrong script. Again, this is a relatively simple Python API. The first step is to load, first import all of the relevant modules, then load the mesh, define the mesh path, load the mesh. Then it will, once the mesh is loaded, it will display the mesh. So you can see this is the same mesh as we previously produced. If I close, it's going to show the mesh that corresponds to the quantum dot region. I'm going to close again and let the simulation run and comment on the code while the simulation is running. It will take maybe a minute. So apart from loading the mesh, what we need to do here is to create a device, which is defined on the mesh. So the device is the main object in which all of the physical quantities and models are stored. And for example, we can set the temperature of the device to 0.1 K using this command set temperature. We can create doping density. So this is a variable that we define for the doping density in this n-dope layer. And then we can set up materials in the heterostructure stack. So the idea is simply to call this new region method of the device for each of the layers that we defined previously and specify a material, which we load from our materials database, and a doping density if it is non-zero. Then we can align the bands across the heterostructure interface, define applied potentials on each of the gates, define a Schottky barrier height because we are going to use Schottky boundary conditions for all of those gates. Those boundary conditions are set here, and we use an ohmic boundary condition for the back gate, so at the very bottom of the structure. The next step, we create and instantiate a nonlinear Poisson solver and set its parameter, for example, the tolerance of the self-consistent loop, the maximum number of iterations. We will create a submesh for the dot region and solve Poisson's equation everywhere in the structure. Save the results, the conduction band edge in VTU format, set the confinement potential from the electric potential that we calculated by solving Poisson's equation, and create a sub-device in the dot region, solve Schrodinger's equation, so create the solver and solve it, and then output the eigenfunctions and print the eigenenergies of the structure. So you can see the simulation has run. We converged in maybe 17 iterations in roughly 1 minute. And we can see now the energy levels of the structure are displayed, and the eigenfunctions and conduction band edge have been saved. So now I can go into this output file and open those VTU files for the conduction band edge and the eigenfunctions. So let me first open the file for the conduction band edge. So I can double click on it. It's a VTU format, so automatically it's gonna launch ParaView. If I click apply, we can view actually the conduction band edge. You can see the color scheme here throughout the 3D structure. So we can easily recognize a pattern that corresponds to the gate layout. And you can also notice that there is a potential well being formed. So you can see blue is slightly negative and red is very positive. You can see a potential well being formed between those gates. If I look at the heterostructure axis here, we can also see a discontinuity in the conduction band edge that corresponds simply to the mismatch. It's a band offset between the materials, so gallium arsenide and aluminum gallium arsenide. So if I go back to the presentation, I'm talking about these discontinuities here. Using ParaView, I can also create a slice in a region that interests me. So I'm going to do Z normal. I'm going to create a slice right below the interface between gallium arsenide and aluminum gallium arsenide. I'm going to click apply, and I'm going to rescale the color plot. And this way we can see, yes, we truly have a potential well where we want it. And it's also slightly negative, meaning it's slightly below the conduction band edge is slightly below the Fermi level, which is set to be 0 by definition in Qtcad simulations, in which we assume thermodynamic equilibrium. Now the question is, does this potential well enable to host bound states? To verify that, I will open the eigenfunctions.vtu file that was produced by solving the single electron Schrodinger's equation. I will click apply. Now what you're seeing is a box that corresponds to the quantum dot region. So that is this region below this rectangle between the gates. And we're not seeing much because all of the action is actually inside the box. So we're going to make a slice again. So let me click on this and click on this and look at the ground state. So you can see now this really looks like a confined state. So we really have a bound state actually in the structure. And I can also show the first excited state. You can see there are 2 lobes. This is what we would expect. The second excited state, the lobes are in the orthogonal direction. So I actually need to do a slice which would be y normal. I click apply. I made a clipping instead. You can see the lobes are formed here. So I hope now to have convinced you that using Qtcad, simple Python scripts can be used to produce simulations of realistic structures, and then using ParaView, we can visualize the results in 3D and help understand if a structure is promising to host spin qubits. So let me now go back to the presentation and go to full screen. I will go back to where I was and follow up with the conversation. Sorry, with the presentation. So I can see. Let's see here. Yeah, so I can see there is a question: is the Schrödinger and Poisson method combined with a non-equilibrium Green's function? So I'd like to answer this question right now. So currently these are equilibrium calculations, so there is no NEGF, but we are working on an NGFKP solver. So this should be possible in the relatively near future. Yeah, so other questions I think I will answer later on at the end of the presentation. So there are many. So what I showed was really just the most basic simulation of electrostatics at cryogenic temperature. As we saw, we converge below at 100 milli-K, and commercially available Qtcad tools. What we've been told by our collaborators is typically they fail to converge below 100K. So this is clearly an advantage in using Qtcad, and because spin qubits are operated at very low temperatures. So we saw this in my ParaView files. There are many other things that one can do once these most basic simulations are done. So namely Poisson and then Schrödinger. For the most simple thing that one can think of is to tune gate voltages and look at how the energy, the electronic structure of the quantum dot responds to those changes. This can be used to calculate the lever arm of a device, the lever arm of a set of gates, which is a crucial quantity for control of those systems. So this, as you can see here, we can see how the energy levels depend on the plunger gate voltages here. And calculate a lever arm by simply making a linear fit. There are, of course, much more advanced features. I mentioned earlier in the workflow or in the models section that we can also solve, we also have the many-body solver that accounts for Coulomb interactions in the structure. So we can use this to calculate chemical potentials. So that is the total energy with n electrons in the ground state minus the total energy with n-1 electrons in the ground state. So more roughly speaking, how much energy is needed to add an electron in the structure. So this is particularly important because it determines if current can flow through a quantum dot. So here I illustrate a system where you have a source, a drain, and a single quantum dot. The blue lines represent chemical potentials, and this actually illustrates the Coulomb blockade effect. So you will only get current flowing through the structure if one of the chemical potentials sits within the bias window between, formed by the source and the drain. And so using Qtcad, it's possible to find the bias configurations in which such currents are allowed, and to find bias configurations that enable to load a single electron in the structure. So here, for example, we have 3 electrons loaded in the structure. So on the right-hand side, I'm showing a Qtcad simulation for the structure that I just introduced, and for 5 plungers, so the gate voltage, the plunger gates of 0.3 volts. We also have quantum dynamics feature, which enables to calculate Rabi oscillations using either spin-orbit coupling or micromagnet EDSR. Here I'm illustrating results for micromagnet electric-dipole spin resonance simulations. The idea is to have a uniform background magnetic field, which will Zeeman split an electron that is confined in this quantum dot. And then in addition, you have a slanting field from a micromagnet, which creates this magnetic field gradient along a perpendicular axis. And a semi-classical picture is that when an electron oscillates back and forth in the structure, for example, because of electric biases. In its frame of reference, it will see oscillating magnetic fields, which can be used by electric dipole spin resonance to manipulate coherently the spin of the structure. So on the right-hand side, I show Qtcad simulations of those Rabi oscillations in this structure. So you can see that if you are able to define the magnetic field throughout the structure, you can find the Rabi oscillation rate that corresponds to a certain gate bias configuration and a certain device geometry. So we can go all the way from the device layout to single qubit control features. And there are, of course, many other unique features of Qtcad. As I mentioned before, it is possible to calculate charge stability diagrams. So using our quantum transport solver, master equation solver, combined with our many-body solver, it's possible to solve for the current that flows through a quantum dot and get those Coulomb diamonds that correspond to, say, 0, 1, 2, or 3 electrons in the structure. We also have a valley coupling tool that enables to calculate valley splitting in a nanostructure, a quantity that is key to operation of spin qubits in silicon. And finally, it's possible to account for classical electric noise in the device and see their effect on Rabi oscillations. And we have, of course, many more features to come.